Tonight we're going to talk about this topic here, the flood. I want to give you a big picture overview of the flood, its mechanism and the evidences, so you can put all the little pieces together that you've probably learned about over the years. And I'll try not to make this too technical, but there are resources that you can follow up on if you want to do a slower version of this presentation. Let me begin by posing the question, how did marine fossils get to be buried in sedimentary rock layers in the Himalayas, high in the Himalayas? In fact, there's ammonite, they're coiled marine fossils, high up in the Himalayas, near the top of Mount Everest. That's a good question, because when we analyse that tonight, you'll find out that the secular scientific community can't really answer that question with all the theories that they have. They think they have the answer, but they don't, as we'll shortly see. The Himalayas consist of folded marine fossil-bearing strata, rock layers, and they were deposited during the flood on the continents. Mount Everest is on the continents, the Himalayas on a continent, and so these marine fossils had to be buried in these rock layers on the continent. And they're only recently elevated. In fact, the Himalayas are still rising, and that would have been at the end of the flood from a biblical perspective. Furthermore, this would have required that the ocean waters had to flood over the continents, which logically follows, of course, from the Genesis flood, and they would have had to carry marine fossils with the sediments, marine creatures with the sediments. Once those layers were in place, there had to be a collision of continents to buckle those rock layers. There had to be some forces at work to buckle those rock layers so as to raise those fossil-bearing sedimentary layers to the heights where they are now found today. Now, some further observations in the real world of what we see that help us start our quest tonight in answering that original question. Most of the Earth's marine fossil-bearing sedimentary rocks are on the continent. Now, you might think, big deal, but that's profound. That's profound if you think about it. Because where would marine creatures live today? In the oceans. Do we find marine creatures being fossilised in the oceans? No. And the secular scientific community believes the oceans flooded over the continents. Why? Because the fossils are on the continents, not in the oceans. And in fact, their absence on the ocean floors implies that the ocean floors are younger than the rocks on the continents. Now, that's important to remember. The ocean basins are younger relative to the continents because the fossils are on the continents from the flood, not in the ocean basins. If the present ocean basins were where the flood was occurring to make fossils, the fossils from the flood should also be in the ocean basins. You see the logic? The ocean floor rocks are younger than the fossil-bearing rocks on the continent. The ocean floor rocks are also different. Most people don't realise that the rocks on the ocean floor are made up of basalt under the veneer of thin veneer of sediments. Therefore, basalt is heavier and denser than the rocks on the continents. And I'll illustrate what this means. That's why the ocean floors are at a lower elevation to the continents. Another observation is that the continents were once joined together in a single supercontinent. And I'll show you in a minute that the idea actually started with a Christian geologist. What we can further observe is that because the ocean floors we have today are younger, they weren't the original ocean floors. The original ocean floors, the pre-flood ocean floors, which surrounded the original supercontinent, have now gone. They've disappeared. You see, these are observations which are significant for us to understand the big picture mechanism of how the flood occurred. Now, the internal structure of the Earth is also important to understand. We know from seismic waves, that's from earthquakes and nuclear explosions where the sound waves travel through the earth, that it's made up of a core, both an inner and outer core, a mantle, and the thin veneer at the outside is called the crust. That's what we live on. And when we look at the density of the densities of those portions, the inner core is of a density between the metal lead and mercury, whereas the Earth's crust is about the density of aluminum. So there's a big difference in densities. That's why the crust effectively floats. It's light and it floats on the mantle underneath. The other thing that's interesting, most people don't realise, as I said before, that there's a difference between the rocks that make up the continents and the rocks that are on the ocean floor. On the continents, we've got sedimentary layers, and if you go to the Grand Canyon, you go down the walls of the Grand Canyon, and you come to crystalline basement rocks of granites and metamorphic rocks, and they extend right down to the bottom of the continental crust. But on the ocean floor, underneath the thin veneer of sediments that you can see there on the left, the diagram on the upper left, underneath are basalts and other related rocks to basalts. So there's a difference in the composition, and there's a difference, therefore, in the density of the rocks. Basalts are heavier than granitic. The average composition of the continental rocks is granitic. It's not all granite, but that's the average chemical composition. Now, this has important consequences. As I said before, the lighter, less dense continents therefore float on the denser mantle beneath them. And it's like blocks of wood floating in water. Where you've got a thicker piece of wood, it actually rises higher and there's more underneath. So in fact, the Himalayas are the highest part on the earth, but they're also the deepest crust because you've got to have a root underneath. For that to ride so high, there has to be more underneath. And this is important to understand. We've built up this idea, this picture of the Earth's structure from studying the earthquake waves and the nuclear explosions, the waves produced by them. And it's verified by lots of other circumstantial evidence. Now, it's because of this that we find the differences between the continents and the ocean floors means that the ocean floor being denser sinks and the continents rise. And so that's why the continental land surfaces are always above sea level, because they rise relative to the level of the sea. Now, you'll understand in a moment why that's very significant and quite profound. And it's a real problem to the conventional scientific community, because how can you get the ocean waters up onto the continents? To bring the sediments and the rock and the critters, the marine critters, up to bury them on the continent. That's the problem we have to answer. Well, as I said before, it was actually an American Christian geologist, Antonio Snyder, who first of all saw the jigsaw puzzle fit between North and South America and Africa and Europe. Trouble was, it was 1859 and it wasn't a very good year to publish another theory. And he couldn't find an English publisher. It was published in French, in Paris. And he saw that jigsaw puzzle fit, and he realised that therefore the continents may have originally been joined together and they spread apart rapidly during the flood. Not continental drift, but continental sprint. And his idea was ignored, and the scientific community took it up in the 20th century, and they robbed it from us. Well, it's time for us to claim it back. Now, the conventional idea in the scientific community today, since the mid-1960s, is called plate tectonics, not continental drift. You'll see why in a moment, because it's not just the continents that are divided and moving around, it's also parts of the ocean floor. So they talk about plates. And so the conventional slow and gradual, or what we call the uniformitarian, that's substitute the word slow and gradual, plate tectonics, it goes something like this. We have slow and gradual drift of continents over hundreds of millions of years. But the sea level during that period has to rise to flood the continents, then fall to re-expose the continents repeatedly many times to deposit the discrete sedimentary layers slowly over millions of years. So you go to the Grand Canyon, you see these different rock layers, and we're going to talk about those on Thursday night, discrete layers, and to put those layers in place where there's millions of years between the layers, the water's got to come up, go back, go up, go back, and so the continent's got to go up and down, up and down, up and down about 7 times. Well, it's hard enough to get it up once, then I have to do it 7 times. So I have to do it repeatedly, and that is a big problem for their viewpoint. Furthermore, as I said, this requires the ocean floor to rise and fall, or the continents to fall and rise many times. And that's a physical impossibility. At today's snail-paced tectonic or earth movement processes, that simply cannot physically explain and achieve this process. Now, it is true that you can divide up the Earth's surface into these tectonic plates. The word tectonic is just a word which means earth movements, more or less. And the boundaries are easy to discover. And this is what the power of this model was in the 1960s. Simply because the boundaries are marked by earthquakes. Makes sense. If they're moving relative to one another, you're going to generate earthquakes. And these boundaries and movements also explain why the volcanoes are where they are. And so that's why there occurred to be a revolution in the earth sciences with this idea of slow and gradual continental movement in the form of these tectonic plates. As you can see, for example, the African plate there in the middle of the screen includes the ocean floor around Africa. And that's why they call them plates, not just continental drift. It's plate tectonic movement. Now, this is what it looks like in a 3-dimensional depiction of these motions, where the ocean floor is sinking under the continent, as you can see on the right-hand side of the screen. We call that subduction. In the middle of that ocean, you can see a mid-ocean ridge. The ocean floor is being pushed apart. That's called seafloor spreading. And where the continent is being pulled apart, it's called continental rifting, like in the East African Rift Zone and in the Jordan Dead Sea Valley. The Earth is being pulled apart. The continent is being pulled apart, and you can see where there are volcanoes in that diagram. And it's all related to these movements of these tectonic plates. What drives this process? Well, it's what goes on underneath the Earth's crust that drives it. Inside the Earth's mantle, we've got motion of rock material, heat and rock material. And so where the ocean floor sinks, it pushes aside mantle material that circulates and comes up somewhere else, as you can see on that diagram. You can see a mantle plume come up with new material and heat. You can see it under a volcano. And so you've got this circulation of material inside the mantle. Now, in conventional thinking, that is a slow and gradual process. But we're going to see that it's impossible to produce what we see on the continents today unless it was catastrophic, a catastrophic process. Now, as I said before, on the continents only, we have thousands of feet of marine fossil-bearing sedimentary rock layers. Now, you'll see diagrams of the fossil record, and everyone thinks that you only get marine fossils at the bottom and you only get mammals at the top. No. Marine fossils are found throughout the fossil record. Testimony that the ocean waters were over the continents throughout the formation of the whole fossil record. And that's important to remember. In many places we have mixtures of marine and continental land-dwelling critters buried together. So, the less dense continental crust floats high and dry above sea level. So today, the sea isn't flooding the continents. So the present can't be the key to the past, can it? If we don't see the continents being flooded by the oceans today, then the present can't be the key to the past. And again, remember, the less dense or lighter continents float on the denser mantle beneath them, so they only sink, that is, those wooden blocks of the continent will only sink if more rock material is added on top of them, okay? You put another block of wood on top of that wood and it will sink, won't it? It'll float lower. But how do you get the material up on top of the continent? If you try it, you can't, it won't go down, okay? It won't go down of its own accord. It's going to keep floating up. So how are you going to get things from the ocean up there if the continent won't sink? Because it won't until it's got more material on top of it. So it's a chicken and the egg question, isn't it? Which came first? Well, here's the answer. The only way to make the sea level rise so the ocean waters flood the continents is to raise the ocean floor upwards relative to the continents. So if the ocean floor rises, the ocean water will also rise and come up onto the continents. Okay, so how do we raise the ocean floor? You can't do it slow and gradually, you have to do it catastrophically. And there's the answer to the puzzle, to the generation of Noah's flood. You see, in slow and gradual plate tectonics, do we see the sea level rising today due to the ocean floor rising and flooding the continents? Do we see vast sediment layers being deposited across the continents today? Do we see marine creatures being buried in vast fossil graveyards on the continents today? No, absolutely not. The answer to those three questions is no, no, no. And yet, that's what had to happen during Noah's flood. As I said a moment ago, the present geological processes of slow and gradual plate tectonics cannot explain, therefore, what happened in the past during Noah's flood. So we need to remember the Grand Canyon is carved into marine fossil-bearing sedimentary layers now a mile above sea level. And in the Grand Canyon, we've got a sandstone, for example. One of the sandstones that forms a cliff is the Tapete sandstone. And it's a very interesting sandstone because when you look down the bottom of at the bottom of the Tapete sandstone, there are boulders up to 15 feet in dimension, in diameter. Now, you can see the person there for scale. And I've put circles around two of the big boulders. 15 feet wide. You need fast-moving water, don't you, to move a boulder that size? A slow-moving river today, not even the Colorado River when it's in flood can move boulders that size. And there's lots of them everywhere you go at the bottom of the Tapete sandstone, which means that it was very catastrophic high-energy conditions which deposited those boulders and the sandstone on top of them. What most people don't know is that sandstone can be traced right across North America. It's that sandstone and its equivalents. Isn't that the sort of evidence you'd expect to find for Noah's flood? Rock layers that went right across continents that were deposited by ocean waters that went right across continents. And that's what we see. In fact, the equivalent of the Tapete sandstone can also be found in southern Israel and in Jordan. It's the same sandstone, the Nubian sandstone, that you find at Petra. The same features as in the Tapete sandstone in the Grand Canyon, halfway around the world. That's what you'd expect to find on the basis of Noah's flood. That's what we find, and it runs counter to what the scientific community understands. Also, we've got a prominent cliff of limestone in the Grand Canyon. The red wall limestone gets its name from forming a red wall. And the cliffs can be seen from one end of the Grand Canyon to the other. And it's full of fossils, like these squid-like fossils called nautiloids, and lamp shells called brachiopods, and sea lilies or crinoids, and they're all broken up and smashed and in layers that are being deposited by fast-moving water. Corals. I mean, that's not the way corals live, all in different angles and directions. They grow on a reef stacked on top of one another. This is not where these creatures lived. This is where they are buried. And they show all the evidence that they've been buried catastrophically. And here's the heads of these corals in this limestone. By the way, the equivalent of the red wall limestone in the Grand Canyon is also found in the Himalayas. You see, there is abundant evidence for Noah's flood if you have biblical glasses. If you stand on the authority of God's word as the true account of the earth's history, then the evidence is plain for all to see. That's why, as we'll talk about tomorrow morning, the scoffers are willingly ignorant of the evidence that's there for all to see. Well, let's now talk about, therefore, instead of a slow and gradual earth movements, let's talk about catastrophic earth movements in the context of the flood. And let's talk about what we call catastrophic plate tectonics, not slow and gradual, but catastrophic plate tectonics. We'll call it CPT for short, catastrophic plate tectonics. Now, in my estimation, it's the only viable model for the global flood that doesn't conflict with real-world observational data. It explains more real-world observational data, integrates big-picture evidences for the flood, as we'll see. And it explains more real-world observational data than the uniformitarian plate tectonics model does, plus much more data that the uniform slow and gradual model can't explain and doesn't explain. And you'll see that in a moment. Now, it's only a model, okay? It needs further development. It has its weaknesses. But models are ideas, practical ideas that scientists put up to try and explain what they observe. And so they're always open to further refinement and development. But this model does explain a lot, and it's exciting how it integrates so much evidence for Noah's flood. Now, let's remember that the flood was not just a global watery cataclysm, but an earth-shattering catastrophic tectonic event. I mean, Psalm 104 says the mountains rose, the valleys sank. There were earth movements, and not just water rising and sinking, as some might think from just reading Genesis 6 through 8. The pre-flood supercontinent, well, there had to be one because it would appear from Genesis 1 verses 9 and 10 that when God formed the seas, he gathered them together in one place. Therefore, the land was maybe in one place. That's where Antonio Snyder got the idea from. And it broke apart, therefore, and separated into today's continents by continental sprint during the flood. This requires both enormous vertical and horizontal earth movements, measured in terms of miles and thousands of miles horizontal. And unfortunately, that's the problem with some of the other models presented by creationists. Some of them talk about the vertical movements, but they ignore the horizontal movements. We've got to be able to explain everything that we see, not just parts of it. And the pre-flood ocean floor, as I said before, would have disappeared during the flood because of these catastrophic plate tectonics processes, which I'm going to explain. Okay, so let's get into the nitty-gritty. Let's start by assuming, and again, we have to have our assumptions, but it's a reasonable assumption that the pre-flood Earth consisted of the same core, mantle, and crust internal structure as we see today. And it's only reasonable that God would have made the earth with that sort of structure because it works very well. All the continental crust was combined originally into one supercontinent, and we've just seen that from Scripture, the possibility that's a good assumption. Now, this is a key point. The surrounding ocean floor crust was cold and denser than the warmer mantle rock beneath it, on which it floated. And because it was floating precariously, it was poised to sink if disturbed. The best illustration is we see a needle made of iron floating on water. The iron in the needle is denser than the water underneath. And if you touch the needle and break the surface tension of the water, the needle will sink. The cold ocean floor is denser. It's made of the same material as underneath in the warmer mantle, but because it's cold, it's denser. The warmer mantle underneath is less dense because of its warmth. Because of the warmth, it's expand, and therefore it's less dense. So you've got something heavier floating on something less dense. So that's why it's precariously poised to sink if disturbed. And that is important. The mantle layer just above the core was also hotter, less dense than the central part of the mantle. That's key aspects, because if it's warmer down the bottom of the mantle, that material is going to more easily rise towards the Earth's crust, the surface of the Earth. Now, when God triggered the beginning of the flood, there's no question that God triggered that God didn't start the flood. That's the implication, isn't it? Because God told Noah exactly when to go in the ark, because he knew in 7 days' time it was going to start. So he superintended exactly when the flood started. So there were 5 processes that simultaneously occurred when God initiated the flood. They're not one after the other, they're all happening simultaneously. Okay? The first is that the ocean floor gets ripped apart and the continents get ripped apart. And the Bible refers to the fountains of the great deep breaking up, Genesis 7:11. The initiation of the flood wasn't the floodgates of heaven opening, but the rifting, the breaking open of the fountains of the great deep, the deep being the earth's internal inside the earth. The deep is also below the continents as well as below the oceans. The earth was ripped apart all around the globe, both on the continents and under the oceans, all at once. The second thing is that where the ocean crust was adjoining the continental crust, that boundary was ruptured, it broke, and the ocean floor started sinking because it was denser than the warmer mantle underneath. So it started sinking or subducting. And so that's exactly the picture we see there in that model. The middle of the ocean basin is ripped apart, where that mid-ocean ridge is. It's being pushed apart, ripped apart, and the ocean floor against the continent on the right is starting to sink or subduct under the continent. So it's like a conveyor belt. Things start to move. Before the rupturing, the top picture there on your left, the oceanic crust was joined to the continental crust. After that rupturing, there's a disconnect between the ocean floor, the ocean crust and the continent. It starts to sink down under the continent, subduct. And of course that means the cold, dense ocean floor, pre-flood ocean floor, is starting to disappear. Now, as a consequence, it's going to have to be replaced. We'll come to that in a moment. And this is how it happens. As the continent is rifted apart, the ocean crust is pulled apart, something's got to come up into the rift, hasn't it? And so what you find is that the warm mantle material underneath rises up to fill the void. That's why you've got volcanoes in the African rift zone, because the African rift zone, East Africa, is being ripped apart and material is coming up to feed those volcanoes. But it's only slow today and very sporadic. But during the flood, it would have been catastrophic. And as you pull it apart, the new rock is going to be basalt, which is going to make new ocean floor. And so in the middle of a continent, you're going to split a continent and you start forming a new ocean floor or ocean basin where there was originally one continent. It gets ripped apart and the rock material that comes up forms a new dense ocean floor because it's not granite, it's basalt, which forms a new ocean floor, and it sinks, so water fills up where it's sunk. Yes, it is complex, but it's easy to follow if you just work through it logically with me. Okay, the third process is as that sinks and that rises, you're going to have material coming, sinking over here, pushing aside the mantle rock underneath. The rifting ocean floor and continental supercontinent is going to provide space for the mantle material to upwell, and so you're going to form this circular flow inside the mantle that I illustrated to you before. The rock going down pushes aside mantle and moves it around, so it's going to come up back to the surface warm. The cold material goes down, warm material comes up. The fourth one is violent supersonic steam jets propelled by steam from the ocean floor and continental rift zones that encircle the globe. What happens? You break open, you do the rifting, hot rock comes up, hot rock is going to interact with the cold ocean water. The hot rock also has water in it, so you're going to have steam generated that's going to be propelled up through the ocean water, catching some of the cold ocean water and taking it up into the atmosphere. And it's effectively the fountains of the great deep bursting open, and as the water goes up, what's going to happen into the atmosphere? It's going to come back down again as intense global rain. And so from the point of view of the observer, the floodgates of heaven were opened. See, in this crack on the ocean floor, you've got this hot material coming up with water, and it's going to produce steam, which is going to rise, going to take some of the ocean water with it. Now, the fifth thing is that the mantle material, magma material, the molten rock material that upwells from the mantle into the drifting ocean floor to push aside the old ocean floor is going to be new, warm ocean floor. Okay? So you're going to replace the old ocean floor with new ocean floor, but it's going to be hot because it's new rock material that's come up. Because it's hot, what's going to be? It's going to be less dense, okay? And therefore it's going to rise, and therefore it's going to push up the water, it's going to push up sea level, and now we can see how we can get the ocean waters to come up onto the continents, because it's going to push up the ocean floor by 3,500 or more feet. So it's going to raise sea level by 3,500 or more feet. And that means that the ocean waters are going to rise up over the continents, exactly as we would expect should happen. So again, you can see this rifting process in these two diagrams, where new molten rock material comes up into these rift zones, these pull-apart areas on the ocean floor and on the continents. And here's in this diagram, you can see on the right where the hot new ocean floor comes up with producing these steam jets, which produces the intense global rain. At the same time, it's pushing aside the cold, dense ocean floor, which is sinking under the continent on the left. As it sinks, it's going to, catastrophically, it's going to happen so quickly, it's going to drag down the edge of the continent. It's actually going to push it down with it, which helps the ocean water as the hot ocean floor is rising the sea level over here. It's going to help to push the seawater up onto the continents. And of course, it's going to take the critters with it and take sediments with it as well. So these 5 things all happen at once. At the moment, the door slams on the ark and the flood starts. Now, how do we know that this is possible? Well, theory, experiments and computer simulations show that tectonic plates can sink only rapidly. Metres per second, tens of feet per second. The crucial physics involves a latent instability in the way hot but solid silicate rock deforms under stress. And the behaviour is non-linear. Once it gets started, it goes faster and faster. And we've known this from laboratory experiments. The result is that once the deformation process starts, continuing application of the stress, pressure on the rocks, increases the rate at which it occurs. And the friction generates heat, which makes the rocks more plastic and able to deform or change its shape, and that decreases the friction, so it moves more rock at greater speed. This is the sort of equipment that scientists use to study how rocks under heat and pressure are affected. And I won't go into the details there, but you can see it on the screen. Pressure is applied, the material is heated, and it's studied how it deforms. And under a microscope, electron microscope, you can see that the rows of atoms disconnect from one another and move relative to one another. And you can see that from the lines of atoms in that photograph there. So once the cold, dense ocean floor slabs start sinking into the warmer mantle, the resulting friction generates heat around the slabs, which makes the surrounding mantle rock more plastic, decreases the friction, so the sinking slabs move faster and faster and faster. There's a feedback mechanism, and we get what we call thermal runaway subduction. It goes faster and faster and faster. Now you'll appreciate when I tell you that this moves at metres per second, or tens of feet per second. And it pulls these slabs or these plates apart, and they start to accelerate to that kind of speed. And we can simulate this on a computer with two-dimensional calculations, with real data concerning how the way the rocks deform. So here's an example. This work was done by my friend and colleague, Dr. John Baumgartner. Here we have the initial start of the experiment in the computer. Blue means cold, red means hot. So at the top there, the top diagram is a cut through the Earth's mantle. The top is cooler than the bottom, which is red. Okay? So within a matter of days, you've got the cold material sinking, displacing the hot material, which rises in another place to the Earth's surface. Okay, as a result of these 5 simultaneously occurring processes, there are 7 outcomes during the flood. Once we trigger it with these 5 simultaneous catastrophic geological processes, we have 7 immediate outcomes. Okay, the first one is the ocean floor and continental plates move relative to one another at rates of metres per second. That's tens of feet per second, separating, moving apart, subducting, sliding past one another, slamming into one another to produce mountain belts. And these processes and outcomes can be simulated, as I said before, in a three-dimensional system in a computer, starting, for example, with a configuration of a supercontinent known as Pangaea. Okay? And here we see 5 snapshots in time, starting at the top left-hand corner when everything's joined together in a supercontinent called Pangaea. The process starts, and you can see the one on the right, they're a little bit apart, then C, D, and E to the bottom, you get the present configuration of the continents. And so that's a drawing. Now in the computer, you can actually play the game of watching it happen. And we're talking about within days, the continents have moved apart dramatically at metres per second. Okay, so it's the first snapshot in the computer. The second snapshot, they're starting to move apart. The third snapshot, you can see the dark outlines of today's continents, how they moved apart. In practical terms, let me talk about North America. If we start with a proto-North America on the left there at the top, and we've got ocean floor that starts to sink with little islands which are volcanic action. What happens is that with time, because of the subduction, you're going to move these fragments together and they're going to collide. And so you're going to add to eastern North America, first of all, what we call the Piedmont terrain, then the Carolina slate belt, And then when it goes further, when Proto-Africa ends up completely colliding with North America, we actually buckle eastern North America to produce the Appalachian Mountains. But as the process continues, that Proto-African continent has tensions in it, and a new rupture occurs, and what happens? You get the formation of the Atlantic Basin, the Atlantic Ocean opens up, and part of the original part of what was Proto-Africa is now left joined to North America. And this is the games that you can play with this kind of modelling to explain different geological areas on the continents. So, for example, we can look at the opening of the Atlantic Ocean basin. Well, we know that you can match things from one side to the other. In the left-hand diagram, there are basalts in South America and Africa which are the same, which line up when you put the continents together. You've got the Appalachian mountain belt with that red streak. When you break them apart, what happens? Well, that one original area of basalts gets split into two. And you can trace where they go onto the two different new continents. The same with the mountains. So the Appalachians in North America are related originally to the Caledonian Mountains of Europe when those continents were once back together again, as we can see that. Yes, those millions of years are not the conventional time frame, not the biblical time frame. This is because I'm using diagrams out of conventional textbooks so that you can see that we can take the data that they present, strip it of its time frame within the flood when these processes were at catastrophic rates rather than slow and gradual. So in the case of the Himalayas, you've got the Indian continent, Indian plate slamming into the Eurasian plate. And I like to illustrate it this way. If the motions were slow and gradual, it's like two cars colliding at 1 mile per hour each. Will they do much damage? But if they're each travelling at 100 miles per hour on each, what's going to happen? You're going to get the Himalayan mountains. You're going to get buckling. So the second outcome is that the earthquakes produced by all these earth movements will generate devastating tsunamis. That's tidal waves. We saw that Indian Ocean one several years ago, and boats were marooned miles inland because the ocean just swept up onto the continent. And that was only 50 foot of earth movement. Imagine hundreds of feet and thousands of feet of earth movements. The tidal waves are going to advance and crash onto the continents, carrying with sediments scraped from the ocean floors and from the slabs that are sinking, in the ocean floor slabs that are sinking inside the earth. And so you're going to get this process of material scraped off as the ocean floor advances. You've got these tidal waves. You've also got the irregular ocean currents as well. You've got the normal tidal currents. So you're going to have a combination of surges going up onto the continents. And this is a simulation diagram of how the ocean waters, as they rose onto the continents, would have circulated to move sediments and to deposit them up on the continents. The third is that the ocean waters and tidal surges carried sediments and marine animals from the pre-flood shallow ocean floors and dumped them up on the continents in rapidly deposited sedimentary layers in which the animals were buried. Okay, these layers were eventually stretched right across the continents because as the waters came higher and higher in each surge, they moved further and further inland until the whole earth was covered. All the high hills under the whole of the heaven and the mountains were covered, totally inundated. So let's illustrate this. Here we have the shallow water marine life on the edge of the pre-flood ocean basins just before the flood in this diagram. We begin the flood and we've got new rock material coming up that's warm. It raises the water level. It moves those marine creatures up onto the land where they are buried with the sediments. And then the ocean waters drop as the process ends, as the ocean floor cools and falls. And so the ocean waters retreat back again, leaving the marine creatures buried high up on the continents. The next outcome is that these successive sediment-laden water surges up onto the continents were driven by these tidal waves, these tsunamis, and daily tidal surges resulted in a continuous sequence of fossil-bearing layers being deposited. Not one and then millions of years later another. It was one after the other with surge after surge after surge. So when you see these rock layers in the Grand Canyon, different types of sediments with different types of fossils, they represent successive surges of ocean water bringing material and critters up onto the continents to bury them in these successive rock layers. At the same time, you would have massive volcanic eruptions. Because all this molten material coming in from inside the Earth, you would have huge volcanic eruptions. And the volcanic rocks would be interspersed between the the fossil-bearing sedimentary layers, and we see that in many places around the Earth. So on the continents, we see now thousands of feet of these marine fossil-bearing sedimentary layers in a continuous sequence. For example, here in the Grand Canyon and to the north up in southern Utah. And we see these basalt areas of huge volumes of basalt, which I mentioned before, which you can trace from one continent to another where they split apart. The conventional community calls these flood basalts, but it's a small f, not a large f. Small f for flood, meaning they came out in a huge catastrophic eruption. For example, in India, they're what we call the Deccan Traps, where these volcanic layers are thousands of feet thick over thousands of square miles. And that can only be explained in catastrophic terms during the flood. Then the sixth consequence is that the fossil record was laid down as animals and plants were progressively swept away and buried by these rising ocean waters. As they rose, they destroyed pre-flood habitats. That's why there's a sequence in the fossils, because as they rose up, different habitats were destroyed. First of all, the shallow water marine creatures, and then lowland creatures, and then mountain creatures. And we can see this in this diagram here. As the ocean waters came up, they would successively destroy different pre-flood habitats, sweeping the creatures away and burying them. And that's why we see that order in the fossil record, where we go from marine creatures to begin with eventually to mammals, as well as marine creatures. Notice, as I said before, there are marine creatures right throughout the record as testimony to that it was ocean waters that produced the fossil record, and it is a dramatic documentation of the Genesis flood. As we can see from this photograph of dinosaur bones found at the Dinosaur National Monument in Utah. Huge animals that didn't just sort of fall over and sort of slowly covered by sand and mud over millions of years. These creatures had to be buried catastrophically, otherwise they wouldn't have been preserved. And then where collisions occurred between these plates, the layers would be buckled, folded and uplifted, and the heat and the pressure would metamorphose the rocks and melt some of them to produce the granites. And that's what we see. For example, as I said before, the Himalayas were formed as the Indian plate slammed into Asia. And the buckling produced those high mountains. Sediments that had been laid down by the ocean waters flooding onto the continents were pushed up thousands of feet and buckled and contorted. And for example, off the west coast of the United States, where the ocean floor was going down, molten material came up, the sediments were buckled, and you get metamorphosed rocks and granites like you see in the Yosemite National Park area in the Sierra Nevadas. Now, these processes would have continued until all the pre-flood ocean floor crust had been subducted. Once it had all gone and been replaced, the driving force would slow down, it would come to a grinding halt. The mantle convection would slow, and eventually the warm material previously at the mantle core boundary would now be moved up to the Earth's surface to form that new crust which was cooling down. Once the thermal runaway episode had stopped, when all that pre-flood ocean floor had been subducted, everything slowed down to today's snail pace. So the snail pace we see today of movement is really the leftover remnants of Noah's flood. Do you realise that? We're still experiencing the effects of Noah's flood today by the leftover volcanic activity and earthquakes. Okay, in this diagram to remind you that the process slowed down when all that blue material was down at the bottom and all the red hot material was up the surface where it cooled to form the new ocean floor crust that we have today. Now, as the new ocean floor crust progressively cooled, it became denser and sank. And so what happened? The mountains rose, the valleys sank, the waters returned. People say, where did the water from the flood go to? It went into these new ocean basins that sank because the rock cooled and sank heavier into the Earth's mantle below. The edges of the continents which had been dragged down also bobbed up like corks to form mountains like the Rockies and the Sierra Nevadas, with the granites and the metamorphic rocks in them. And of course, that's what we see off the west coast of the United States, where you have still some remnant volcanic activity in Mount St. Helens through that area, and you have the granites in the Yosemite National Park. It's where the continental edge was affected by the end of the flood processes after everything had been finished being dragged down. And it's the reason why we have the high mountains like the Himalayas. The falling sea level and rising mountains caused the floodwaters to drain off the continents catastrophically. And when they drained off catastrophically, what would they do? They would catastrophically erode to produce new canyons, taking sediment out to the oceans, depositing on the continental shelves where we find it at the edge of the continents today. So, for example, the Grand Canyon and the area to the north in southern Utah, Zion National Park, Zion Canyon, Bryce Canyon, were all carved as a result of the receding floodwaters. And that's why we've got the Grand Canyon today. Now, because the ocean waters were warmer at the end of the flood, remember all that hot water coming from inside and all the volcanic activity, the ocean waters would have been warmer, there would be more evaporation. What would that mean? More moisture in the atmosphere. The warm moisture would circulate to the poles where it would cool and it would fall as snow. And so the ice age after the flood was a direct consequence of this process during the flood. Warmer ocean water, and we've got evidence that that was the case. The oceans were warmer in the past, and because of that, that's the only way you get an ice age, by the way. You don't need cold conditions for an ice age. You need warmer oceans. Colder conditions doesn't cause more evaporation. You need warmer conditions. And so the ice age was a direct consequence of the flood. And so we can see in this diagram the ice sheets that formed at the poles. As a result, the sea level sank as a result of moisture going up into the atmosphere, generating land bridges so that animals and humans could migrate after the flood and after the Tower of Babel. And all followed in God's plan, if this process is a good way of understanding how the flood occurred. And here's another interesting thing as we get to the end of our time. Because this means that the cold material at the top sank to the bottom and the warm material rose to the top in the Earth's mantle, we call that the mantle was overturned. Now, if that only occurred 4,500 years ago, there should still be evidence that that occurred. And so it was predicted in 1994 that because of this catastrophic process during the flood, only having occurred recently, there should be still evidence of cold pre-flood ocean floor slabs at the bottom of the Earth's mantle, because there wouldn't be time for them to warm up and assimilate with the mantle. Guess what? In 1997, seismic images found those cold ocean floor slabs. A direct prediction made by a creation scientist was verified. And that's the power of any model. If it makes predictions and those predictions are verified, it gives you confidence in your model. And so in the scientific community, they came up with the evidence to verify that the creationists were correct, creation scientists were correct about catastrophic plate tectonics during the flood. There's another diagram of the imaging of the warmer and colder portions of the Earth's mantle that represent the leftover remnants of what happened during the flood when the mantle was overturned. Well, let's have some conclusions. Number one, conventional slow and gradual plate tectonics cannot explain how the ocean waters flooded over all the continents to deposit the sediments, burying the marine fossils in layers that stretch right across the continents, even in today's high mountains. Number two, all flood models but one cannot explain the enormous vertical and horizontal earth movements during the flood that occurred during the flood, miles and thousands of miles respectively, as an original supercontinent broke apart and separated into today's continents. Thirdly, only the catastrophic plate tectonic model explains far more real-world observational data and integrates the most big-picture evidences for the flood. Fourthly, catastrophic plate tectonics is an inevitable consequence of a pre-flood cold, dense ocean floor surrounded by the supercontinent floating on a warm, less dense mantle. Fifth, there were 5 catastrophic processes that all occurred together: the ripping apart of the ocean floor in the supercontinent, the rupturing of the ocean crust connected to the edges of the continents so that it sank underneath the continents that were forming as a result of the rifting apart. We had mantle-wide flow of material so that warm material upwelled to the Earth's surface. Supersonic steam jets were produced to induce intense global rain. The new warm ocean floor rose and therefore raised the sea level. And as a consequence, the automatic outcomes during the flood were there were metres per second plate motion. Earthquakes generated devastating tsunamis that advanced right over the continents. Fossil-bearing sedimentary layers were rapidly deposited across the continents. Successive tidal surges and tsunamis rapidly deposited whole strata sequences. Massive volcanic activity added huge volcanic layers. The fossil record was progressively laid down in an explainable manner, an order, a pattern. Plate collisions produced mountain belts with metamorphic rocks and granites. When all the pre-flood ocean floor was subducted, 7, all these processes slowed, sea level fell as the new ocean crust cooled and sank, the waters retreated off the continents, eroding canyons, and the flood ended. The warmer post-flood ocean waters inevitably generated the post-flood ice age. Unassimilated, that is unmixed, cold material still is found at the core mantle boundary today, can only be explained by recent catastrophic plate tectonics during the flood. And finally, this idea or this model, while it's practical and it explains a lot of things, we need to keep in mind that it still needs to be refined. It is, after all, only a human conjectural model. It has great explanatory power, and further research will improve its explanatory power. Our ultimate standard is the biblical record of the flood, and that's what we measure these models against. And in this case, we find that this model confirms what the Bible describes for us about what occurred during the flood.